Hey guys, well, I hope you had a great weekend. Sorry I can't be there this morning. I'm at a meeting down by the airport. And today's a really important day, which is kind of a bummer. So I'm going to do my absolute best here to make sure that you learn what it is we're doing and what Friday was all about, because you might remember I left you on a little bit of a cliffhanger. And then I will see you tomorrow. By the way, tomorrow we'll talk about all things related to your test. So don't stress. Okay, so on Friday, you and I were having a really good conversation about four functions that I gave you. And all I did really was ask you simply to graph those functions. And so you might remember by the end of the period, you had graphed those four functions. However, I do need to point out they didn't look like this, because you might recall all you had was the anchor points. So if you look at the green, the blue, the purple, and the red function, and you see the anchor points, those are really the only ones that you could see on your screen. The other ones were kind of hidden. And so many of you thought that all of these functions were actually lines, when of course if you look at the functions, the red one over here is definitely a linear function, but the blue one is quadratic, the green one is absolute value, and then j of x, the purple one down here, is cubic. And so graphing those functions using an input-output table, it really didn't work very well. So Evan made a suggestion. Evan said, hey, what if we zoomed out, like using a really big coordinate plane and graphed all of our points on that coordinate plane? Because if we zoomed out, then we could definitely see the shape of them. I think I joked about doing a 200 by 200 grid. And that's definitely true. We could see all of the points that way. But because I only gave you these 5 inputs, it still would not show all of the important features of the graph. Like if you look at this blue quadratic up here, here's one of the points I gave you, and here's another one. And I don't even know where and there's another one. And those 3 points don't make the graph look very much like a quadratic. You need some symmetry there. So one of the other things that you mentioned was, well, what if we just changed the input values over here so that we knew we could capture all of the important parts? And that's actually a really great idea. The problem is you don't know where those points are. Like for instance, if you look on this green absolute value, I'm sure that it would have been really helpful if I would have given you, I don't know, -9 and -8 and -7 and -6 and -5 and maybe 4 and maybe 3 and maybe 2 and maybe 1. Like maybe those would have been really good, because then you could have seen, oh wow, it goes down this way and then it pops back up there. I guess -4, -3, -2, -1 would have been better. And so we're faced with a problem now because we have all these new functions and we don't know how to graph them, because an input-output table is not going to capture the important pieces of those functions. So this is where we are resorting back to what we learned last unit about parent functions. So let's say, for instance, that I have this particular parent function. This is the quadratic parent function. And you'll notice that I have graphed the anchor points of this parent function. Now, every single parent function has 4 different ways that you can make changes to it. The quadratic has 4 different ways. The power exponential function has 4 different ways. Linear function has 4 different ways. Absolute value function has 4 different ways. And fortunately for you and I, all 4 of those ways to change the functions work the same for every single function. For instance, this is a souped up, super duper quadratic function. And what I've done is I've put in 4 different levers. These levers, the A lever, the B lever, the C lever, and the D lever, are all different ways that you can change the parent quadratic. And each one of these levers, A, B, C, and D, controls a different type of movement for the quadratic graph. Like for instance, if I just set the C lever in motion, I'm sure you're able to see what the C lever might do for this particular function. The C lever is in charge of moving this function to the left and to the right. And then back to the left and back to the right. Now, what's most important about the C lever, other than the fact that it moves it left to right, is to understand what values move it to the right and what values move it to the left. So you'll notice right now the C value is positive, and now the C value is negative. And now the C value is positive, and the C value is negative. See, the C value is responsible for moving any graph, quadratic, absolute value, power exponential, left and right. When the C value is positive, it's going to be moving that graph to the right. When the C value is negative, it's going to be moving that graph to the left. The one thing, though, that is a little bit strange is that if you look at our levers, A, B, C, and D, there is one lever that starts negative. Or in other words, in the formula, that value is already negative. And that's the C value. So I'm going to stop this here. I'll go ahead and stop it at 3. And we know that because the C value is 3, it's going to move the parent function to the right 3 units. However, it is a little confusing because when it's written in the equation for the parabola, like for instance, you'll notice this guy down here has a C value of -3. That actually makes it go to the right, because the C is already negative in the formula. So a C value of 3 does move the graph to the right, but it looks like x minus 3. So that's a horizontal movement, left and right, but this here is to the right 3 units because the formula is negative. Similarly, the D value will move that parabola up and down. So for instance, if your C value is negative, it will move it that many units down. Pardon me, your D value. If your D value is negative, it will move it that many units down. And if your D value is positive, it will move it that many units up. Now, the A value and the B value are confusing and complicated, and they have lots of little intricacies about them. So we're just going to be talking about the C value and the D value today. Again, the C value moves it left and right. The D value moves it up and down. So that's how you can move or graph a quadratic function using the parent function as the base. So for example, I'm going to turn these guys off. And let's go back to the parent function. So there's our parent function. And I'm going to go ahead and put a function in here. Let's say f of x equals x plus 2 squared minus 5. Where do you think that graph will be located? Again, we have a C value here and a D value. I know that this is the C value because it's inside of the grouping symbol. So that's my left and my right movement. And then this guy here is my up and my down movement. So let's turn it on. So this is now 2 units to the left and 5 units down, because my C value is -2. You might be looking at that and think to yourself, no, Mr. Hammond, you made a mistake. It's +2. No, my C value is actually -2, because remember, in the formula, it starts negative. And then my D value is -5, and so that goes down 5. All right. Go ahead and ask the sub for one of the transformation sheets, and I will see you again in just a second.